Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Fiber optic troubleshooting requires a very different approach from copper-based diagnostics. While electrical signals can be checked with basic testers and LEDs, fiber optics deal with light, something invisible to the human eye and often undetectable without specialized equipment. Many fiber faults leave no visual cues, no audible noise, and no flashing lights. As a result, diagnosing issues in fiber networks demands a precise, methodical process supported by dedicated tools. You can't rely on intuition or guesswork. Fiber is high performance and high sensitivity, and that means accuracy matters more than ever. In this episode, we'll cover the specialized toolset required to troubleshoot and verify fiber optic networks. We'll look at advanced diagnostics like optical time domain reflectometers, light source and power meters, insertion loss testers, and visual fault locators. You'll also learn why fiber cleaning is essential, how connector mismatches can degrade performance, and what symptoms suggest damage or misalignment. Fiber requires a different mindset, one focused on measurement, visual inspection, and documentation. It's a domain where precision determines whether your network runs at full capacity or fails silently. One of the most powerful fiber diagnostic tools is the Optical Time Domain Reflectometer, commonly known as an OTDR. This tool works by injecting short pulses of light into a fiber and measuring the reflections that bounce back. These reflections occur when the signal encounters a splice, connector, bend, or break. The OTDR measures how long it takes for the light to return, calculating the distance to the fault based on the speed of light through the fiber. It also measures loss at various points, giving a detailed map of where degradation occurs along the run. This allows technicians to locate problems with pinpoint accuracy. OTDRs are used extensively during both installation and repair. When installing new fiber runs, they help confirm the integrity of splices, connector ends, and cable segments. They also provide a performance baseline for future comparisons. During troubleshooting, OTDRs can quickly identify whether a break exists, whether a bend is too sharp, or whether a splice was poorly made. They are particularly useful for long-distance links where visual inspection isn't feasible. Without an OTDR, locating a fiber break buried under a concrete floor or stretched across a building would be nearly impossible. Light source and power meter tools form another crucial part of fiber diagnostics. A light source sends a calibrated optical signal down the fiber, while the power meter measures the strength of that signal at the other end. This confirms whether the link is within acceptable signal loss ranges. By comparing the transmitted power to the received power, you can calculate how much loss has occurred. This is essential when diagnosing performance problems that don't involve total failure. A link might pass traffic, but operate poorly due to excessive attenuation. Light source and power meter readings help quantify that degradation. Insertion loss testing is the process of measuring how much signal is lost as light passes through the cable, connectors, and splices. This value is expressed in decibels or dB. Lower loss values are better and indicate cleaner, more efficient connections. If the loss is too high, the signal may not reach the endpoint with sufficient strength, especially over longer distances. Insertion loss testers help verify that connectors were terminated correctly and that splices are clean and well aligned. These tools are often used during installation certification, where documented proof of signal quality is required before handoff. A simple but effective fiber testing tool is the Visual Fault Locator, or VFL. It works by sending a red laser beam through the fiber, which is visible to the naked eye. VFLs are not used to measure performance, but to quickly identify breaks, bends, or misaligned connectors, especially over short distances. If a connector is cracked or if a cable is kinked too tightly, the red light will leak out, revealing the fault location. VFLs are helpful in field conditions, especially for patch panel verification, jumper testing, or short patch cord inspection. While limited in range and diagnostic depth, they are fast, portable, and easy to use. Fiber inspection microscopes allow technicians to inspect the physical condition of fiber connector end faces. These microscopes can be handheld or integrated into electronic testers with built-in cameras. A clean, undamaged fiber end should appear as a smooth, polished surface with no debris or scratches. Even tiny dust particles, unseen to the eye, can disrupt light transmission or cause reflections that interfere with performance. Microscopes help identify contamination or physical damage that could otherwise go unnoticed. Before any fiber connector is inserted into a port or test tool, it should be inspected under magnification. Cleaning is arguably the most important but most neglected part of fiber maintenance. A single speck of dust on a connector can reduce signal quality or prevent a link from coming up entirely. Technicians must use specialized tools such as lint-free wipes, alcohol-based cleaners, and fiber cleaning pens to clean end faces properly. Never blow on a fiber connector. Use your shirt sleeve or touch the tip with your hand. These practices introduce more contamination or damage. Every fiber connector should be cleaned before insertion and before every test. This isn't optional, it's required to maintain signal integrity and extend component lifespan. Fiber breakage symptoms vary depending on the severity and location of the fault. A complete break, such as a severed cable, results in no light transmission, causing the link to fail outright. A high-loss condition may result from misaligned connectors, bent fiber beyond its minimum radius, or poorly made splices. These issues lead to excessive attenuation and degrade performance. Intermittent problems often stem from bends that exceed the rated bend radius, which cause momentary light loss depending on cable movement or environmental factors. Knowing what symptoms correspond to each failure type helps pinpoint the cause quickly. Matching the correct connector and cable type is another critical part of fiber diagnostics. Fiber connectors come in various shapes and locking mechanisms, including LC, SC, and ST types. Each connector has a matching port type and can be either simplex or duplex. Additionally, cables must match the transceiver and panel types, single mode or multi-mode, and the correct core size. Using the wrong type or mismatching single mode and multi-mode equipment results in failed links or high signal loss. Visual inspection and proper labeling help prevent these errors during setup or when tracing connectivity in complex environments. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Once you've completed testing with tools like OTDRs and light meters, it's critical to document the results. This is more than just good practice. It's often required in professional environments where service-level agreements or compliance standards are in place. For fiber installs, saving OTDR traces provides a baseline against which future troubleshooting can be compared. This trace shows the cable's condition at the time of installation, including splice points, losses, and total length. Likewise, insertion loss test data should be recorded and labeled by location, device ID, and date. These logs are vital during project sign-off, post-incident analysis, or when a technician needs to revisit the site months later. Proper fiber handling practices must always be followed to prevent performance degradation or outright damage. Fiber is extremely strong when pulled lengthwise, but it is highly vulnerable to crushing and bending. Kinks and tight curves violate the minimum bend radius and cause microfractures or permanent damage. Always use manufacturer guidelines when routing and coiling fiber. In large installations, this means observing spool radius requirements and avoiding cable tie tension that pinches or distorts the cable. Fiber slack should be coiled loosely and protected in trays. Unused connectors should always be capped with dust covers to prevent contamination and protect against damage from ambient particles. When troubleshooting fiber signal loss, it's important to rule out each possible cause in a methodical way. Start by confirming that the connectors are fully seated at both ends. A slightly loose connector can break the light path or cause significant reflection, leading to high attenuation or erratic behavior. Next, check insertion loss with a power meter. If the signal loss is higher than expected, it's time to inspect the connectors for contamination or wear. A dirty or scratched end face is one of the most common issues. If all else fails, an OTDR can reveal whether the fault is within the cable run itself. Excessive connector losses, poor splices, and mid-span bends can all be diagnosed using the right test tool. Fiber safety must always be taken seriously. The light used in single-mode fiber, especially at wavelengths like 1310 or 1550 nanometers, is invisible to the human eye, but still potentially harmful. Never look directly into a fiber port or cable, even if the link light is inactive. Use a power meter to detect live signals instead. Post warning signage in areas with active optical transmission equipment, especially where equipment is being actively patched or cleaned. Always wear appropriate personal protective equipment, PPE, including eye protection when splicing or cutting fiber strands. Broken fiber shards are extremely sharp and nearly invisible, posing both puncture and ingestion hazards if mishandled. A critical distinction during troubleshooting is knowing whether the problem is at layer 1, the physical fiber connection, or layer 3, such as IP routing. Just because a fiber link light is active does not guarantee that the network path is functional. A working link only confirms that the light signal is strong enough to establish connection, not that traffic is being routed properly. This is why layer 1 testing should always precede deeper packet or route tracing. Once the light path and signal quality are confirmed and insertion loss is within spec, only then should the technician escalate to checking VLANs, routes, or firewall rules. Avoid wasting time on upper layer diagnostics when the light signal itself is flawed or absent. Many enterprise switches and routers now include vendor-specific diagnostics for their optical ports. These platforms can report real-time receive RX and transmit TX power levels measured in dBm. These values are often available via the command line interface, CLI, especially on equipment that supports SFP or QSFP modules. A value outside the normal operating threshold, either too low or too high, may generate warning or alarm messages. These readings can also indicate when a transceiver is beginning to fail. Some switches even support digital optical monitoring features that can alert administrators through S&P traps or system logs when signal levels degrade, helping to catch problems before users notice them. The Network Plus exam includes questions specifically focused on fiber troubleshooting tools and methods. You might be shown a scenario involving a non-functional fiber connection and asked to select the appropriate tool, such as a visual fault locator for local testing or an OTDR for long-distance diagnostics. You may be asked to identify connector types by image or match them to their use cases. Exam scenarios might also describe symptoms of light loss and ask you to determine whether the problem lies in a dirty connector, a bend radius violation, or a transceiver mismatch. Understanding each tool's function and when to use it will directly improve your performance on these questions. To summarize the key fiber diagnostic tools covered, the OTDR is your go-to for mapping and locating faults over long distances. Power meters and light sources help quantify signal strength end-to-end. Visual fault locators are ideal for short-range testing and pinpointing visible breaks or bends. Microscopes allow inspection of connector end faces, ensuring they are clean and undamaged. Cleaning tools like fiber wipes and pens are used before every connection or test. Collectively, these tools form a comprehensive approach to troubleshooting and maintaining high-performance fiber networks. Each plays a unique role, and using them correctly ensures minimal downtime and consistent link quality. Fiber optic diagnostics require precision, planning, and discipline. You can't guess your way through fiber troubleshooting, and shortcuts usually lead to poor results. Always begin with physical verification. Clean, inspect, and connect carefully. Measure signal loss, check for reflections, and verify connector types. Use logs and vendor tools to monitor live link health. Document your findings so they can inform future work. Treat fiber with the care it demands, and it will reward you with speed, reliability, and uptime. Ignore it or try to treat it like copper, and you'll find yourself chasing invisible problems. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.